Welcome viewers. In this video we'll see the definition of inductance and derivation of inductance of coaxial cable, that is a underground cable or normally a cable. First we'll see the inductance. So the inductance is a property of the coil which does not permit sudden changes in the current. So the inductance is nothing but a coil. The main property of the inductor is it will not allow sudden change in current. Current will increases gradually or decreases gradually. So it is defined as flux linkage per unit current. That is L equal to N pi by I. This N pi is nothing but flux linkage divided by current. So this inductance based on three parameters: number of turns in the coil, flux linking with the coil, and current flowing through the coil. N pi by I. The unit is Henry. Right? So flux linkage per unit current. Now we'll see the inductance of a coaxial transmission line. So inductance of coaxial cable. What is coaxial cable? It contains two conductors, inner and outer conductor. The axis is same for both the conductor. That's why it is called a coaxial cable. It has the radius A. The internal conductor radius is A. External conductor radius is B. It's a underground cable, black color underground cable having two conductors. By using that we can transmit the single phase power. One is used for phase, one is used for neutral, another one used for neutral. And also it is simply, it can take the inductance of a cable. Simply we can take it as inductance of a cable. That refers a underground cable. Overhead cable separate derivation is available. So this one refers underground single phase coaxial cable having two conductors A and B. Radius is A and B. Now we can refer the diagram. So this is a coaxial cable. So the axis is same. The axis is common for both inner and outer conductor. So this is the inner conductor with radius A meters. This is the outer conductor with radius B meter. Right? Inner conductor and outer conductor. The axis will be common. That's why it is called a coaxial cable. The surface area is ds. The current I is flowing through this conductor. We consider 1 meter length of cable. The length of the cable is 1 meter. For calculation purpose, we consider one point P, which is in between A and B, greater than A and less than B. At that the radius is rho meters. We consider one point P at a radius rho meter, that is in between A and B. Right? So the one straight conductor is available. Current flowing through the conductor is I meter. This is the inner conductor with radius A. This is the outer conductor with radius B. This is the surface area. The length of the conductor, the length of the cable or conductor is 1 meter. We consider one point P at a distance rho meter from the axis of the cable. So this diagram also same. It's the inner conductor with radius A, outer conductor with radius B. Point P is located at a distance rho meter. So both are same. So inductance of a cable or inductance of a coaxial cable or inductance of cable with the two conductor, for all this is the same derivation. Another derivation, inductance of solid conductor, means only one conductor will be there, that is separate derivation. And inductance of two wire transmission line, that is overhead transmission line, that is separate derivation is available. So this refers the underground cable having two conductors. Now we'll see the description. The conductor in the cable carries a steady current of I. The current I is flowing through the conductor. The radius of inner and outer conductors are A and B. Right? The radius of inner and outer conductor is A and B. We will see the further descriptions. Now we consider the differential area ds at a distance rho meter at a distance rho meter from point P. So this is not a point P. Consider a differential area at point P with radius rho meter from the axis of the cable. So this one. Consider 1 meter length of cable. We consider 1 meter length of the cable. The magnetic field intensity at point P can be obtained by Ampere's law. By using Ampere's law, we can find the magnetic field intensity. Thereby, we will find the inductance. Our aim is to find the inductance. First, we will find the magnetic field intensity. Then, step by step, finally, we will calculate the inductance of this cable. So, based on the Ampere's law, what is given? Work done equal to current. Integral H dot dl equal to I. That is the statement given by Ampere's law. So, in this derivation, H dot 2 pi rho equal to I. What is 2 pi rho? Integral H dot dl equal to I. So, integral dl is L. L is nothing but circumference of that cylinder, the closed loop, 2 pi rho. We consider the radius rho. The inner and outer radius is A and B. In between, we consider one segment called rho. So, H dot 2 pi rho equal to I. From that, H equal to I divided by 2 pi rho. Right. So, this is the magnetic field intensity. From that, magnetic flux density B can be calculated as B equal to mu H. There is a relation available between B and H, right? So, B equal to mu H. So, from magnetic field intensity, we can calculate the magnetic flux density. B equal to mu into H. H is nothing but I divided by 2 pi rho. So, that B equal to mu I divided by 2 pi rho, right? So, this is the equation number 1. Now, we got the expression for B, magnetic flux density. But in general, the magnetic flux density is given as d pi by ds. The general formula, flux per unit area. Magnetic flux density means flux per unit area. Take this equation number 2, right? So, this left hand side are equal. So, we can equate the terms available in right hand side. These two terms are we can equate because these two left hand side, these two parameters are equal, right? So, from equation 1 and 2, we can equate this d pi by ds equal to mu I divided by 2 pi rho, right? Both the equation 1 and 2, the right hand side terms are equated, right? From that, d pi equal to mu I divided by 2 pi rho, this ds is brought in this right hand side into ds, right? The ds is available now here. So, d pi equal to mu I divided by 2 pi rho. What is ds? D rho into dz, that is radius into height. This rho refers the radius, z refers the height. We consider 1 meter length of cable, right? The radius is rho. Actual radius is A and B, right? Okay. So, this is the flux linkage due to small segment, small point, the rho. If we want to find the total flux linkage can be obtained by integration. By integrating on both the sides, we can get the total magnetic flux, right? I will go for the integration. So, integral d pi equal to double integral, because here we have two terms, radius as well as the length. So, radius varies from A to B. We need to find the inductance between inner and outer conductor, that is radius of inner conductor to radius of outer conductor. So, that A to B is a limit for this radius. For the distance, for the length is 0 to 1. We consider 1 meter length of cable, right? So, the limit for the radius is A to B, that is nothing but radius of the inner and outer conductor. The limit for the length is 0 to 1, because we consider 1 meter length of cable. Now, this mu I divided by 2 pi is constant. Only we have 1 by rho d rho into dz, right? With a limit A to B and 0 to 1. Now, we can go for the integration of 1 by rho. So, with that, pi equal to mu I divided by 2 pi is constant. Integral 1 by rho is log rho with a limit A to B. Integral dz is z with a limit 0 to 1, right? 1 by rho, integral 1 by rho is log rho, and integral dz is z with a limit 0 to 1. Now, we can substitute the limit. mu I divided by 2 pi, you substitute the limit log b minus log a, upper limit minus lower limit. And here upper limit 1 minus 0. So that is nothing but 1. So pi equal to mu I divided by 2 pi. Log b minus log a can be written as log b by a. That you know very well, log b by a. This become 1, right? Now our aim is to find the inductance. So bring this I in the denominator. So what will happen? Pi divided by I equal to mu divided by 2 pi log b by a. Right? What is pi divided by I? Pi divided by I is nothing but inductance. Already we discussed that. L equal to n pi by I. Here n is 1. So it is pi by I. Pi by I can be written as inductance. That is mu divided by 2 pi log b by a. So the final expression for inductance of this cable, underground cable, is mu divided by 2 pi log b by a. The unit is Henry per meter, because we consider 1 meter length of cable. So this expression for 1 meter length of cable, so the unit is Henry per meter. Suppose if you want to find the entire length, inductance of L meter length of cable is given by, that is nothing but L equal to mu divided by 2 pi log b by a into L. You have to multiply with length of the cable, so that the total inductance of total cable, length of the cable, can be obtained. In this case the unit will be Henry. Here we consider full length of cable, right? So the final expression is inductance L equal to mu divided by 2 pi log b by a into L for the entire length of the cable. So in this video we discussed about the definition of inductance and derivation of the inductance of cable, coaxial cable or underground cable having two conductors. Thank you. Welcome viewers. In this video we'll see the inductance of coaxial line with solid conductor. Only one conductor available. In previous video the inductance of coaxial cable with two conductors is available. In this video having only one solid conductor. So this diagram shows the coaxial transmission line with a solid conductor of radius a meter. Right? So refer the diagram. We have one conductor is available. Only one solid conductor. The radius is a meters. If you want to transmit the single phase power, we need one more conductor. For single phase power we need like this, one more conductor is needed. So here we have only one conductor. For transmitting single phase power like this, we need two conductors. So the flux, total flux is, now we have pi 1 and pi 2, sum of pi 1 and pi 2. What is pi 1? The flux due to this solid conductor itself is nothing but pi 1. Flux linkage due to the solid conductor. So due to single phase we are having two conductors, so the flux between these two conductors is pi 2. Flux linkage between two conductors. Right? So in this derivation we consider only one conductor, solid conductor with radius a. If you want to transmit the single phase power, we need two conductors. So the flux is nothing but flux due to the solid conductor pi 1, flux between these two conductors pi 2. We assume that one more conductor is available nearby. So the flux is pi 1 plus pi 2. Right? So we need to find pi 1 then pi 2. For calculation purpose we consider one point P. Consider a point P at a distance of r meter radius which is less than radius a. Right? We consider one radius r radius, which is less than a. The radius r is less than a meter, the radius of the conductor. That means the point P is located inside the conductor. Not outside, it is inside the conductor. The point P is located inside the conductor with a radius of r meter which is less than a. So at point P we will see the derivation. So our aim is to find the inductance of the solid conductor. First we will find magnetic field intensity, then flux. From flux we can find the inductance, because inductance L equal to n pi by I. Right? So we start with the magnetic field intensity. What is magnetic field intensity from Ampere's law? I divided by 2 pi a. A is nothing but radius of the conductor. But here we assumed one radius r. So we are multiplying with the ratio r by a. What is r? What is a? A is nothing but radius of the conductor. R is, we assumed one point P which is less than a. So if the r is 50% means we'll get 50% of ratio here. If r is 0.7 is 70% means we'll get 70% will be multiplied. For example, a is 10 meter, r is 5 meter mean 5 by 10, it's 1 by 2. 50% will be multiplied together. In order to make the ratio between r and a, we are multiply with r by a. Suppose a and r both are equal, it got cancelled. Otherwise the ratio will be multiplied. So this is due to Ampere's law. Integral h dot dl equal to I. So h equal to I by integral dl, that is 2 pi a, circumference. So after this what we have, IR divided by 2 pi a square. Here one a is available, here one a available. So 2 pi a square. IR divided by 2 pi a square. So from magnetic field intensity we will find the magnetic flux density B. What is B? B equal to mu h. One relation is available. B equal to mu into h. So that mu into h is nothing but IR divided by 2 pi a square. So B equal to mu IR divided by 2 pi a square. So now we got the expression for magnetic flux density B. But magnetic flux density, one more formula is available, general formula. D pi 1 equal to B into A. Right? That is B equal to pi by A, so that d pi equal to B into A. Flux density equal to flux divided by area, so that flux equal to flux density into area. This pi 1 refers flux density due to solid conductor alone. Then flux linkage between two conductors, pi 2 we will calculate later. Right? So d pi 1 equal to B into A. What is B is available here, mu IR divided by 2 pi a square. So here also we multiplied by ratio r square by a square. Actually it is pi r square divided by pi a square. Due to area we are multiply with pi. This pi got cancelled, so r square by a square into dr. Right? We are going to differentiate with respect to radius. The length of the conductor we assumed as 1. So only we have the radius r. Now we got the expression for d pi 1. So d pi 1 equal to mu naught I r cube divided by 2 pi a power 4 into dr. After simplifying this we got this value. So this d pi 1 is the flux of the solid conductor due to small radius r. We assumed one point P at a radius r. If we want to get the total flux, the entire flux linkage can be obtained by integration. By integrating on both the side we will get the total flux linkage. Then what is the limit for that? Limit is 0 to a. That's a is nothing but radius of the solid conductor. Right? So the radius increases from 0 to a. So the limit is from 0 to a. Now integrate on both the side. Integral d pi 1 equal to integral 0 to a mu naught I r cube divided by 2 pi a power 4 into dr. So d pi, integral d pi 1 is nothing but pi 1. So this is a total flux. That is equal to mu naught I divided by 2 pi a power 4 is constant. Only we are going to integrate r cube into dr. This r cube we are going to integrate only the term r cube with a limit 0 to a. Now we'll go for the integration. So mu naught I divided by 2 pi a power 4 constant. So integral r cube is nothing but r power 4 by 4. Right? Integral r cube is r power 4 by 4. Now we need to substitute the limit a and 0. So mu naught I divided by 2 pi a power 4. This r is replaced by a power 4 by 4 minus 0. Lower limit is 0. So what is that? That is nothing but mu naught I divided by 2 pi a power 4. A power 4 by 4. This 0 is available. So a power 4 for a power 4 got cancelled. Right? So what we got? Pi 1 equal to mu naught I 2 pi into 4 is 8 pi. Pi 1 equal to mu naught I divided by 8 pi. So this pi 1 is nothing but flux due to solid conductor alone, right? Pi 1. Now we need to find pi 2 value. What is pi 2? Flux linkage between two conductors. Here we have only one conductor, but single phase we need one more conductor. We assume that nearby one more conductor is there. The flux linkage between these two conductors is pi 2. What is this value? Mu naught I divided by 2 pi log B by A. So this derivation available in a previous video. The inductance of a cable or inductance of coaxial transmission line with inner and outer cylinders. From that we are referring this value. The flux linkage between two conductors available in the previous video, you can refer. So from that we are taking this value, mu naught I divided by 2 pi log B by A. So now we got the two values, pi 1 and pi 2. Pi 1 due to solid conductor alone, pi 2 between the two conductors, right? Now we'll go to the total flux. Total flux is pi 1 plus pi 2. So the total flux equal to pi 1 plus pi 2. Pi 1 is mu naught I divided by 8 pi plus mu naught I divided by 2 pi log B by A, right? So pi 1 and pi 2 are added together. So mu naught I divided by 2 pi we can take it as common, right? So here mu naught I by 8 pi is there, 2 pi is taken outside, so we got 1 by 4, 2 into 4 8, plus this mu naught I 2 pi is taken outside, only we have log B by A, right? So pi equal to mu naught I divided by 2 pi 1 by 4 plus log B by A. This is the flux value, but what we need is inductance, right? So bring this I in the denominator, right? Bring the I in the denominator, so that pi divided by I equal to mu naught divided by 2 pi of 1 by 4 plus log B by A, right? This I is brought into denominator. What is pi by I? Pi by I is nothing but inductance. N pi by I is the formula. Here N is 1. So pi by I is nothing but inductance. So that is equal to mu naught divided by 2 pi 1 by 4 plus log B by A. So this is the total inductance of a solid conductor having only one conductor. By referring one more conductor, assuming one more conductor available nearby, right? So mu naught divided by 2 pi 1 by 4 plus log B by A. A is nothing but radius of the conductor. The B is nothing but distance between the conductor. This B refers distance between the conductors, right? So now we got the expression for inductance of a solid conductor. In this video we discussed the inductance of solid conductor, right? Thank you. Welcome viewers. In this video we'll see the inductance of two-wire transmission line. This two-wire transmission line means the overhead transmission line. There are two conductors available. In previous videos the underground transmission line is available. With a solid conductor one derivation is available. With coaxial line with two conductors, inner and outer conductors, one more derivation also available in previous two videos. That two videos refers the underground cable having two conductors and one conductor. But this derivation refers the two-wire transmission line, overhead transmission line. So this conductor A is available. This is conductor B. The conductor A, the current flowing is plus I. For conductor B, minus I. The radius of the conductor A is small a. The radius of the conductor B is small b. The center to center distance between the conductor is d meters, right? So we have two conductors A and B with the current plus I and minus I. Radius small a and small b. The distance is d meters. So the total inductance is nothing but the loop inductance between conductor A and B is nothing but LA plus LB. Inductance due to conductor A, inductance due to conductor B. L equal to LA plus LB. Now we'll see the description. Consider two conductors A and B of radius small a and b respectively and separated by a distance d meter. Right? We are considering two conductors A and B with radius small a and b. The distance is d meter. The conductor A carries the current of plus I and conductor B carries the current of minus I. So one is forward path and another one is a return path. Right. Now we'll see the inductance of a conductor A. The total inductance of conductor A. What is total inductance? So we consider one conductor A. Nearby one more conductor is there. So the flux is due to conductor A and flux between conductor A and B. There are two flux will be available in conductor A. Flux due to conductor A itself and flux between conductor A and B. That is available in the previous video. The inductance of a solid conductor. From that we are referring this expression. So this expression is nothing but inductance of a total inductance of a conductor A. Right? Mu naught divided by 2 pi 1 by 4 plus log d by A. This A is nothing but radius of the conductor A. D is nothing but the distance between conductor A and B. Right? So this inductance is due to two fluxes. One is flux due to conductor A itself, flux between conductor A and B. Based on that we got this expression. This explanation detailed video available in previous video. The inductance of solid conductor. So this refers the inductance of a conductor A. Then inductance of conductor B. Similarly we have mu naught divided by 2 pi 1 by 4 plus log d by B. What is B? Radius of the conductor B. D is nothing but the distance between the conductors. Right? Now we got the expression for LA and LB. The total refers inductance due to flux due to conductor A and flux between A and B. That's why it is written as total. So the total inductance now nothing but LA plus LB. By adding these two we will get the loop inductance. Loop inductance of a transmission line. So the loop inductance of the transmission line is L equal to LA plus LB. We can add both the values. So mu naught divided by 2 pi of 1 by 4 plus log d by A plus mu naught divided by 2 pi. This is not 4 pi, it's a 2 pi of 1 by 4 plus log d by B. Right? So the A refers radius of conductor A, B refers radius of conductor B. This D refers distance between the conductors. Now we can take mu naught divided by 2 pi as a constant. So 1 by 4 and this 1 by 4 plus log d by A plus log d by B. So you can add this 1 by 4 plus 1 by 4, that is nothing but 1 by 2. So the loop inductance, total inductance of this two wire transmission line is mu naught divided by 2 pi of 1 by 2 plus log d by A plus log d by B. So this is the final expression for inductance of two wire transmission line. Now based on this we will solve one problem. So evaluate the loop inductance per kilometer of a single phase transmission line. Right? We need to find the loop inductance per kilometer. It's given as per kilometer of a single phase transmission line comprising two parallel conductors spaced 1 meter apart. The distance between the conductor is 1 meter and the radius of these two conductors is 0.8 centimeter and 1 centimeter. Right? So the radius of first conductor available, radius of second conductor available, distance between the conductor also available. Right? We'll see the given data. So the D, distance between the conductor is 1 meter. Radius of the first conductor is 0.8 centimeter, that is equal to 0.8 into 10 to the power minus 2 meter. The radius of the second conductor B equal to 1 centimeter, that is equal to 1 into 10 to the power minus 2 meter. So what is the loop inductance? Just now we discussed LA plus LB, that is nothing but mu naught divided by 2 pi 1 by 2 plus log d by a plus log d by b. This mu naught is constant 4 pi into 10 to the power minus 7 plus 1 by 2. The d value available here and a and b value also available. Now we'll substitute the value one by one. Now this value is substituted. Mu naught is nothing but 4 pi into 10 to the power minus 7. Mu r is 1. We assume that r divided by 2 pi into 1 by 2 plus log d by a. D is 1, a is 0.8 into 10 to the power minus 2 plus log d by b. D is 1, b is 1 into 10 to the power minus 2. Right? This 4 pi available here, 2 pi available, got 2 times got cancelled. This 1 by 2 is nothing but 0.5. The value of this is nothing but 2.097. The value of this log is 2. So we have 2 into 10 to the power minus 7 of 0.5 plus 2.097 plus 2. Right? By simplifying this value, what we got, inductance is 9.19 into 10 to the power minus 7 Henry. The total inductance of this loop inductance of this transmission line is 9.19 into 10 to the power minus 7 Henry. So in this video we discussed the inductance of two-wire transmission line, overhead transmission line. We got the derivation and we solved one problem. The inductance of solid conductor and inductance of the cable having two conductors available in previous videos, you can refer. So the totally 3 derivations available. Inductance of two conductors underground, inductance of solid conductor, inductance of two-wire transmission line. Thank you. Welcome viewers. In this video we'll see the inductance of solenoid and toroid followed by the problems. First we'll see the inductance of a solenoid. A solenoid is nothing but a electromagnet. One iron rod is available. Over the iron rod coil is winded. When the current is flowing through the coil, it becomes electromagnet. Right? So solenoid is an electromagnet. It is formed by winding few turns over an iron rod. You refer this diagram. So this is iron rod over which the coils are winded. If the current is flowing through the coil, it becomes the electromagnet. Now we are going to identify what is the expression for inductance of this solenoid. Consider the solenoid with length L meters. In general, the inductance L is given by L equal to N pi by I. The general formula for inductance is N pi by I. But the flux pi can be written as mmf divided by reluctance. Actually, reluctance equal to mmf divided by flux. From that we got flux equal to mmf by reluctance. This mmf is nothing but N into I, number of turns into current. These are all only general formulas. Then the reluctance is nothing but very similar to resistance. So it is L by mu A. Resistance means rho L by A. Here L by mu A. Resistivity, here we have the mu. So this mu A can be go to the numerator. So what will happen? Ni mu A divided by L. The flux pi equal to N pi mu A divided by L. Now we can substitute this pi value in the inductance formula. Inductance L equal to N pi by I. So N by I into pi. This pi is where we are going to replace this value. Ni mu A divided by L. Right? N by I into pi. Pi value is replaced with this expression. So I got cancelled. So what we have? N into N. N square mu A divided by L. Right? So the inductance of a solenoid is N square mu A divided by L. All the formulas are general formulas, not specific to the solenoid. Right? General formula we substituted and we got this value. From this expression, inductance of a solenoid is directly proportional to square of number of turns and permeability. Right? It is directly proportional to square of number of turns and permeability. And also it is proportional to area of the coil divided by length of the coil, A by L also. Now we'll go to the toroid. We'll see the derivation of inductance of a toroid. So what is toroid? So if a long solenoid is bent in the form of ring and thereby closed itself, it becomes a toroid. The solenoid is a lengthier. If the length is solenoid, if the two ends are joined together and form a circle, form a ring, then it is called a toroid. So this is the toroid. It is available in the form of ring. The solenoid is a long iron rod. This is closed iron rod. The two ends are closed and form the ring. Right? So if the long solenoid is bent and two ends are joined together, then it becomes a toroid. So in this toroid, the coils are winded here. So these coils are available. So due to the ring form, this inner radius is called Ri, internal radius. Up to this point is a core, internal radius of the core. Up to the end is a external radius of core, internal radius Ri, external radius Re. So in between these two, this is represented by the dot lines. Rm, mean radius. Rm is mean radius, sum of Ri plus Re divided by 2. The internal radius and external radius added divided by 2 will give the mean radius. Right? So we have the iron rod is available in a ring form. Coils are winded. Internal radius is Ri, external radius is Re. This dotted line in between internal and external is called a mean radius. That is Ri plus Re divided by 2. Right? So Lm, what is Lm? Mean length. One lengthy solenoid is bent in the form of ring. So the length of the solenoid is nothing but circumference of this toroid. Because the lengthy wire, the lengthy solenoid is available, that is closed together and form the ring. So the length of the solenoid is nothing but circumference of this toroid. L equal to 2 pi m. The circumference is 2 pi m. Here we are referring the mean radius. Right? So Lm equal to 2 pi Rm. Then the small r is nothing but radius of this coil. Here the coils are available. These radius refers the radius of the core. The small r refers the radius of the coil. Then what is the area of the coil is pi r square. Area of the coil is pi r square. Right? So this is the detail about that. Now we'll see the description. Let us consider a toroid of internal radius Ri and external radius Re. A toroid is provided with uniformly distributed winding of a large number of closed spaced turns. Right? The uniformly distributed winding is available with large numbers. The flux line in the toroid may be treated as a number of concentric circles. Right? The flux lines are in a concentric circle. It follows in a concentric circle manner. So with this we will go for the derivation. So in general the inductance L equal to N pi by I. Very similar to previous solenoid. Same thing we are following. L equal to N pi by I. But the flux can be written as mmf by reluctance. That is reluctance equal to mmf by flux, so that flux equal to mmf by reluctance. This mmf is nothing but N into I. The reluctance, that is very similar to resistivity. L divided by mu A, here we are referring Lm, mean length. Lm divided by mu A. So this mu A will go to the numerator. So pi equal to Ni mu A divided by Lm. Right? We got the expression for flux. Now we can substitute the flux in this inductance. N by I into pi. This pi can be replaced by this Ni mu A divided by Lm. So inductance equal to N pi by I. So L equal to N by I into pi. Now we can replace this value. Ni mu A divided by Lm. Very similar to solenoid, what we discussed earlier. Only thing here we replaced L as Lm. So this I got cancelled. So it become N square mu A divided by Lm. Right? It is very similar to solenoid also. Now we are going to substitute the value of area and mean length, right? The area is nothing but pi r square. Area can be replaced by pi r square. Similarly, the mean length is nothing but 2 pi rm. Only this is the difference between the solenoid and toroid. We are going to replace these two values. So L equal to n square mu. This A is replaced as pi r square. This Lm is replaced as 2 pi rm. The pi got cancelled. So what we have, n square mu r square divided by 2 rm. Right? We are getting the expression in terms of radius of the coil and the mean radius of the core, rm. Right? So the inductance of the toroid is L equal to n square mu r square divided by 2 rm. N square mu r square divided by 2 rm. So we got the expression for inductance of solenoid and inductance of toroid. Based on that, we'll see the problem. We'll go to the first problem. The problem one is the magnetic circuit comprising a toroid of 500 turns and area of 6 centimeter square and mean radius 15 centimeters and carries a current of 4 ampere. Right? Carries a current of 4 ampere. So the number of turns is 500. Area is 6 centimeter square, that is 6 into 10 to the power minus 4 meter square. The mean radius means rm, 15 centimeter, that is 15 into 10 to the power minus 2 meter. The current is also given as 4 ampere. So these are all the given data. This mu naught is constant, 4 pi into 10 to the power minus 7. We need to calculate the value of reluctance, mmf and flux. Right? We'll see these values one by one. So first we'll see the reluctance. Reluctance S equal to L divided by mu A. Very similar to resistivity. The L is nothing but 2 pi rm. The length is nothing but circumference of the toroid. 2 pi rm divided by mu A. So 2 into pi into rm is given, mean radius is 15 into 10 to the power minus 2 divided by mu is nothing but 4 pi into 10 to the power minus 7. The area given as 6 into 10 to the power minus 2. So this 6 into 10 to the power minus 4 area is given centimeter square, while converting meter square it is 10 to the power minus 4. So after simplifying this, what we got, S equal to 12.5 into 10 to the power 8. It is very similar to resistance. The unit will be the ohms. Right? So after simplifying, the reluctance S equal to 12.5 into 10 to the power 8. Now we'll go to the mmf value. This mmf is nothing but n into I, number of turns into current. Number of turns is 500, current is 4 ampere, so mmf will be 2000 ampere turns. Very simple, directly we substituted. Right? The mmf equal to 2000 ampere turns. Then we'll calculate the flux. Flux pi equal to mmf by reluctance. So mmf is 2000, just we calculated. Then reluctance is what we calculated, reluctance as 12.5 into 10 to the power 8. Right? So 2000 divided by 12.5 into 10 to the power 8. So after simplifying this, what we got, flux equal to 1.6 into 10 to the power minus 6 Weber. Right? So now we got the value of reluctance, mmf and flux. Now we'll go to the second problem. So in the second problem, a toroid is also based on the toroid having 1000 turns. Number of turns is 1000 and mean radius 20 centimeter and radius of the coil 2 centimeter. Right? Number of turns available, mean radius and area of the coil is, radius of the coil is available. We need to find the self-inductance, inductance of the toroid, having two different conditions with air core. With air core means the mu r value will be 1. Right? With iron core, for that the relative permeability is given, mu r equal to 800. Right? So we need to find the self-inductance value for first one is with air core, for that mu r equal to 1, then iron core, for that mu r equal to 800. Right? We'll see the data, given data, number of turns is 1000. Mean radius is 20 centimeter, that is 20 into 10 to the power minus 2 meter. Then radius of the coil is 2 centimeter, that is 2 into 10 to the power minus 2 meter. The mu r is constant, 4 pi into 10 to the power minus 7. Right? Now we'll go to the first condition with air core, mu r equal to 1. Air core means it is mu r value will be 1. Now we'll see what is the expression for the inductance of a toroid. The inductance of the toroid is mu naught mu r n square r square divided by 2 rm. Just before we got the derivation for this inductance of a toroid. So mu naught is 4 pi into 10 to the power minus 7. Mu r value is 1, air core. The number of turns is 1000 square, right? This is also 1000 square. Into r square. R is 2. 2 into 10 to the power minus 2 square. Divided by 2 into rm, mean radius. 2 into 20 into 10 to the power minus 2. Right, now we substituted all the values. After simplifying, what we got? 1.257 millihenry. Milli means 10 to the power minus 3. 1.257 into 1.257 millihenry. Now we'll go to the second division with iron core. For that the mu r value is given as 800. All the values are same, only we need to replace mu r is 800. So inductance of toroid is mu naught mu r n square r square divided by 2 rm. Mu naught is 4 pi into 10 to the power minus 7. Here mu r is given as 800. Iron core with the 800. The problem itself it is given. Then n square. The n square value is 1000 square into 2 into 10 to the power minus 2 square divided by 2 rm. 2 into 20 into 10 to the power minus 2. So after simplifying, what we got? 1 Henry. It is nearly equal to 1 Henry. Right? So now we got the expression for value of inductance with air core and iron core with a mu r value of 800. So in this video, we discussed the inductance of solenoid, inductance of toroid, and 2 problems based on the toroid. Thank you all. Welcome viewers. In this video we'll see the energy stored in inductor and energy density of the inductor. First we'll see the energy stored in inductor. Let us consider this inductor is available. It is connected with the DC supply. It is connected through switch and the ammeter. When the DC supply is given, the current will flowing through the inductor. So due to rate of change of current, EMF is induced in the inductor. See the direction, the induced EMF is opposing the supply voltage. This opposition is converted into work done, that is nothing but energy stored. The opposition of the induced EMF by the voltage source is converted into energy stored in the inductor. Right? So an inductor is available, energized with the DC supply through the switch and ammeter. When the DC supply is given, the current will flowing through the inductor. Due to rate of change of current, EMF is induced in the inductor. That EMF will oppose the supply voltage. So the work done by the DC source against this opposition is converted into energy stored in the inductor. So the work done is equal to energy stored. So the details are given. Ammeter is S is nothing but switch. V is the DC voltage source. E is the induced EMF. L is the inductor. So the description is available. When a DC voltage is applied to the coil, the current increases exponentially. Due to change in current, an EMF is induced in the inductor. The direction of induced EMF is such that it opposes the applied voltage in the closed loop. There is a opposition between induced EMF and applied voltage. So the work done by the DC source against the opposition is stored in the form of energy in the inductor or magnetic field, right? So this work done is nothing but done by the DC source against the opposition, that is converted into energy, right? So the induced EMF in the inductor, the induced EMF in the inductor is nothing but E equal to L di by dt. It's a normal general formula. E equal to L di by dt. Now dW is the work done to increase the current by I. What is the work done? Increasing the current from 0 to I. That is the to the current di. So by law of conservation of energy, work done is equal to the energy stored. This work done is nothing but energy stored. Both are equal, right? So this is the EMF induced. In this, the energy stored is nothing but to need to increase the current by the di value, so that the increasing the current is the energy stored, that is equal to the work done. Now we'll see what is the work done. So the energy is given as power into time. The general formula for energy is nothing but power multiplied by time. This energy is equal to the work done. Just now we discussed the work done is equal to the energy. So the energy is represented as dW, work done. This dW represents the work done by small current. By integrating, we'll get the total work done. So the power is nothing but voltage into current, EMF induced into current, into time is dt, right? This EMF induced in the inductor is L di by dt. Just now we discussed this formula, L di by dt into I into dt. So this dt got cancelled. So what we have? dW equal to Li into di. Right. So this is the work done due to the small current di. Work done, dW means small work done by the small current. So the total work done to establish the current of I can be obtained by integration. So by integrating on both the side with a limit, we can get the total work done. So integral dW equal to integral Li into di. What is the limit? The work done is nothing but increasing the current from 0 to maximum value of current I. So the limit is from 0 to I. The work done is nothing but increasing the current from 0 to I. Now we'll go for this integration. So integral dW equal to W, that is equal to, this L is constant. Only we need to integrate 0 to I into di. We need to integrate only I. So W equal to L, this integral I is nothing but I square by 2. Right, integral of I is I square by 2. We need to substitute the limit 0 to I. So W equal to L, substitute the upper limit I square by 2 minus lower limit is 0. So that W equal to L I square by 2. So that can be written as W equal to half Li square. So that is the energy stored in the inductor. W equal to half Li square. So this I represents the energy stored in inductor, means current is increasing gradually or current is decreasing gradually. The charging, the inductor is storing the energy or discharging the energy, means current increases or decreases gradually. In case of capacitor, the work done is nothing but half CV square. The voltage in capacitor, charging and discharging, means the voltage is increasing or decreasing gradually, right? So the inductor W, energy stored equal to half Li square. Now we'll see the energy density of the inductor. Now we'll see energy density. So the energy density is nothing but energy stored per unit volume. So the density means always we can refer either length, area or volume. Here we are referring volume, right? Density, how much density for a given volume, right? So the energy density is energy stored per unit volume. So for that, first we'll start with the energy stored. Energy stored in the inductor. Energy stored in the inductor is half Li square. Just now we discussed half Li square. In this, what is the inductor? Inductor value, general formula N pi by I. Now we'll substitute this L, replace this L with N pi by I. Therefore energy stored equal to half Li square. L is nothing but N pi by I into I square. So 1 I got cancelled. So half n pi into I, right? So the energy stored is half Li square. In this, L is replaced by n pi by I. At the time 1I got cancelled, we got half n pi into I. In order to get the volume, we are going to multiply and divide by the term length L, right? We are going to multiply this expression and divide by the length L, so that energy stored equal to half n pi by I into L divided by L. So while multiplying and dividing, the originality will not change. Now rewrite this 1 by 2. This n into L is written separately, n into L. Remaining pi I divided by L is rearranged, right? N into L is written here, pi I divided by L is written here. So n into L is nothing but number of turns into length is nothing but a volume, right? So that is written as pi I divided by 2L into volume. Number of turns multiplied by length is nothing but a volume, right? So now we can see that. Now bring this volume in the denominator, this left hand side. Energy stored by volume equal to pi I divided by 2L, right? This volume is brought in the denominator. What is energy stored by volume? Is nothing but energy density. Energy stored by volume is the energy density, that is equal to pi I divided by 2L. The unit is joules per meter cube, because it is divided by volume, it is meter cube, joules per meter cube, right? So the energy stored in the inductor is nothing but pi I divided by 2L, joules per meter cube. Now we'll see the energy density of the solenoid. So the energy stored in the energy density of the solenoid, right? And this energy density is nothing but energy stored per unit volume. So first we will refer the energy stored in the inductor. Energy stored equal to half Li square. In that, what is the inductor value? The previous derivation we refer the general formula, L equal to n pi by I. Here we are referring inductor of a solenoid, right? Because we are going to find energy density of the solenoid, right? So the inductor of the solenoid is nothing but mu n square A by L, right? We need to replace this inductor expression with inductor of a solenoid, mu n square A by L. So that energy stored equal to half Li square. L is nothing but mu n square A by L into I square, right? So in order to get the volume, here also we are going to multiply and divide by the length L, right? Multiplied and divide by the length L. So that energy stored equal to half, that is mu n square A divided by 2L into I square divided by L into L, right? We are going to multiply and divide by the term L. Now rewrite this mu n square divided by 2L into I square. A into L is written separately, right? A into L, area into length. Remaining terms are written here, mu n square, this I square divided by 2L. Here 2L is available, L, here one more L is available, L square. A into L is rewritten. What is area into length? Area into length is nothing but volume. Area refers two parameters into one more parameter. Three parameters means it is a volume, right? Breadth into height, we can refer breadth into height in the area. Into length, length, breadth, height means it is a volume, right? Now energy stored equal to mu n square I square divided by 2L square into volume, right? Now bring this volume in the denominator. This volume is brought into denominator. So energy stored by volume is nothing but energy density. That is mu n square I square divided by 2L square, right? This is L square. Joules per meter cube, right? So this is the expression for energy stored in the solenoid. Previous one is the energy stored in inductor in general. This is specifically for a solenoid, right? Now we'll see one problem based on the solenoid. So in this problem, a solenoid with 200 turns, the number of turns equal to 200, 3 millimeter long. The length of the solenoid is 3 millimeter, that is 300 into 10 to the power minus 3 meter, right? the millimeter is converted into meter, and 20 millimeter in diameter, right? The diameter is 20 millimeter, then radius will be 10 millimeter. That is converted into meter, 10 into 10 to the power minus 3 meter, right? The number of turns available, length is available, diameter available. From that we calculated radius. The current is 600 milliampere. 600 into 10 to the power minus 3 ampere. Milliampere means we need to multiply with 10 to the power minus 3. Right? What is then? We have the constant mu naught equal to 4 pi into 10 to the power minus 7. Right? What we need to calculate? We need to calculate inductance of this solenoid and energy stored in the solenoid. Right? Energy stored as well as inductance value. We will find this one by one. So the inductance of the solenoid is L equal to N square mu A by L. Inductance of a solenoid is, just now we discussed about that, N square mu A by L. Right? This A is nothing but pi r square, because we are having the radius available, so the area is nothing but pi r square. So N square mu pi r square divided by L. Now we will substitute all the values. The number of turns is 200 square into mu. Mu is nothing but mu naught. Mu r value is 1. So mu naught is 4 pi into 10 to the power minus 7 into pi r square. Pi into r square. R is nothing but 10 into 10 to the power minus 3 square. Divided by L. Length is nothing but 300 millimeter. That is 300 into 10 to the power minus 3. Now all the values are substituted. By simplifying this, what we got? 5.263 into 10 to the power minus 5. The unit is Henry. So the inductance of the solenoid is 5.263 into 10 to the power minus 5 Henry. Right? Now we'll find the energy stored in solenoid. Energy stored. What is the formula for energy stored in general? Half Li square. Right? We got the derivation half Li square. So half into L. L is nothing but, just now we calculated 5.263 into 10 to the power minus 5 into I square. I is 600 milliampere. So 600 into 10 to the power minus 3 square. Right? So by simplifying this, what we got? 9.4 into 10 to the power minus 6 joule. Right? The energy stored is given in joules. So 9.4 into 10 to the power minus 6 joules. Right? So now we calculated inductance of the solenoid, energy stored in the solenoid. So in this video we discussed about energy stored in inductor or magnetic field. Then energy density of the inductor. Then energy density of the solenoid. Based on that we discussed one problem based on the solenoid. The inductor value as well as energy stored in solenoid. Thank you. Welcome viewers. In this video we will see the derivation of self-inductance, mutual inductance, coefficient of coupling, followed by the problem. First we will see the self-inductance. The self-inductance refers having only one coil. Mutual inductance means having two coils. So from Faraday's law, changing current will produce an induced EMF in the circuit. Due to rate of change of current, EMF is produced. That EMF will oppose the change in flux. So this is the phenomena. This phenomena is known as a self-inductance. So when the current is flowing through, due to rate of change of current, the EMF is induced. That EMF will oppose the rate of change of flux. So this is the phenomena is known as a self-inductance. Now we'll see the diagram. So consider the coil with n number of turns. So due to self-inductance we are having only one coil with n number of turns. It is connected through the AC supply. V equal to Vm sin omega t. AC voltage is applied to the coil. When the AC voltage is applied, what will happen? The current will flowing through the coil. Right? A coil with n number of turns available, it is energized by the AC voltage. When the AC voltage is given, the current I is flowing through the coil. This current is rate of change of current. Due to AC voltage, this current is rate of change of current. Due to rate of change of current, flux is produced in the coil. The flux is developed in the coil. This flux also rate of change of flux. Due to rate of change of flux, EMF is induced in the coil. Right? So, n number of turns the coil available, voltage is applied, current is flowing. Due to rate of change of flux, due to rate of change of current, flux is produced. This flux also rate of change of flux. So, due to that, EMF is induced in the coil. So, this EMF is depends upon the flux and also depends upon the current, because the flux is produced from current. So, V is depends upon flux as well as the current. Right? So, their details are given here. V equal to Vm sin omega t. I is the current. N is number of turns. Pi is the flux. V is the induced EMF. Now, we will see the derivation. What is the self-inductance of the coil, right? So, we need to remember two things. This V is depends upon flux as well as current, right? So, the description is given. If the AC voltage is applied, current will flowing through the circuit. Due to rate of change of current, flux phi is produced in the coil. Due to rate of change of flux, EMF is induced in the coil, right? So, voltage is applied, current is flowing. Due to the rate of change of current, flux is produced. Due to rate of change of flux, EMF is induced in the coil. Now, we will see what is what is this EMF. So, this induced EMF is proportional to rate of change of current. V is directly proportional to di by dt. So, while equating, we are introducing a constant L. L is nothing but self-inductance. So, V equal to L di by dt. That is equation number 1. Right. So, this induced EMF is proportional to current. From that, we got the equation V equal to L di by dt. You take this equation number 1. Now, we will see the flux. What about the flux? We will see that. From Faraday's law, this induced EMF is also proportional to d pi by dt, rate of change of flux. From Faraday's law, it is clearly states that the due to rate of change of flux, EMF is produced. So, this V is directly proportional to d pi by dt. So, while equating, we introduce the constant N, because the flux is depends upon the number of turns in the coil. So, V equal to N d pi by dt. You take this equation number 2. So, we have one equation. V is directly proportional to L di by dt. Equation 2 is N d pi by dt. So, the left hand side is equal. So, we can equate the terms available in right hand side, right? So, from equation 1 and 2. So, from equation 1 and 2, we can equate L di by dt equal to N d pi by dt, because left hand side is equal. So, the terms available in right hand side is equated. So, this dt got cancelled. L di equal to N d pi. So, from that we can write L equal to N d pi by dt. Right, L equal to N d pi by dt. If permeability is constant, we will take, if the permeability is constant, what will happen? This equation become L equal to N pi by I. Right. The inductance equal to number of turns flux divided by current. L equal to N pi by I. This is the expression for self-inductance. So, the definition what is given, the inductance is defined as the rate of total magnetic flux linkage to the current through the coil. The inductance is defined as the rate of total magnetic flux linkage to the current through the coil. Now, we will see the mutual inductance. So, mutual inductance, where two conductors are available, two coils are available, coil 1 and 2, they are coupled together. Mutual inductance happen between two coils. So, we are here consider two coils, coil 1 and 2, they are coupled together. Refer this diagram. So, this is coil 1, this is coil 2. The number of turns in coil 1 is N1. The number of turns in coil 2 is N2. The coil 1 is energized by the supply, AC supply. The coil 1 is given with the AC voltage V1. When the voltage is applied, what will happen? The current will flowing through the coil 1, I1. The current I1 will flowing through the coil 1. So this current is rate of change of current. So due to rate of change of current, flux pi 1 is produced in the coil 1. So this coil 2 is placed nearer. So part of the flux link with the coil 2, that is pi 1 2. Pi 1 is the flux produced in the first coil. Part of the flux link with the second coil, that is pi 1 2. That is pi 1 2 is nothing but flux linkage from first coil to second coil. This flux is also rate of change of flux. So due to that, EMF is induced in the second coil. So this EMF is depends upon this flux pi 1 2. This pi 1 2 is depends upon pi 1. This pi 1 is depends upon I1. So this V2 is depends upon pi 1 2 in the second coil and I1 in the first coil. That is an important thing. Flux in the second coil and current in the first coil. Due to the current only this flux is produced, right? So we have two coils with n number of turns, N1 and N2. Coil 1 is energized by the AC voltage. So the current I1 will flowing through the coil. Due to this rate of change of current, flux pi 1 is produced in the first coil. The flux is linking with the second coil, that is pi 1 2. Due to rate of change of flux, EMF is produced in the second coil. This EMF is depends upon flux in the second coil and current in the first coil, right? I will see the description. What we discussed, that is given as a description. The AC voltage is applied to coil 1 and current I1 is flows through the coil 1. Due to rate of change of current, flux pi 1 is produced in the coil 1. The part of the flux pi 1 link with the coil 2, that is pi 1 2. Due to this rate of change of flux, EMF V2 is produced in the second coil. So this induced EMF is proportional to the current in the coil 1, I1. Now we'll go to the derivation. So the EMF induced in the second coil is proportional to current in the first coil. V2 is directly proportional to dI1 by dt. So while equating, we are introducing constant M. M is nothing but mutual inductance. So V2 equal to M dI1 by dt. So the EMF induced in second coil is proportional to the current in the first coil. So we got the equation 1. From Faraday's law, what is V2? V2 is directly proportional to d pi 1 2 divided by dt. Flux in the second coil. D pi 1 2 divided by dt. While equating, we introduce the constant number of turns in the second coil because pi 1 2 is depends upon number of turns. So V2 equal to N2 d pi 1 2 divided by dt. This is equation number 2. Right? So now we have two equations. Equation 1 is V2 equal to M di1 by dt. Equation 2 is V2 equal to N2 d pi 1 2 by dt. This left hand side is equal, so we can equate the terms available in right hand side. So from equation 1 and 2, M di1 by dt equal to N2 d pi 1 2 divided by dt. So this is depends upon the current, this is depends upon the flux. So dt got cancelled. M di1 equal to N2 d pi 1 2. From that, M equal to N2 d pi 1 2 divided by di1. Right? If the permeability is constant, then we can take M equal to N2 pi 1 2 divided by I1. Right? So we got the expression for mutual inductance N2 pi 1 2 by I1. So this is the flux linkage in the second coil, current in the first coil. So that is the important definition in the mutual inductance. This mutual inductance depends upon flux linkage in the second coil and current in the first coil. So we got one expression. Suppose if we'll go in a reverse order. Suppose the coil 2 is energized by the AC voltage and EMF is induced in the first coil. then what will happen, we'll see that. We'll follow the same derivation. Similarly, if flux pi 2 1 is produced by the second coil, current I2 in the EMF V1 is, right? Coil 2 is energized. Current I2 is flowing through the coil 2. And flux pi 2 1 is produced in the first coil and EMF V1 is produced in the first coil. Just it is reversed. Coil 1 is energized and EMF induced in the second coil, first case. Second one, coil 2 is given with the AC supply and coil 1 is produced with the induced EMF. So just we can change the terms. Now V1 equal to di2 divided by dt. The EMF induced in the first coil is based on the current in the second coil, di2 divided by dt. Here it is reverse. V1 is now changed into V1. di1 changed into di2. So V1 equal to m di2 divided by dt. You take this equation number 3, right? I think you are able to understand. Now we are energizing the second coil and EMF is induced in the first coil, right? So from Faraday's law, this V1 is proportional to d pi 2 1 divided by dt. Here pi 1 2, first coil to second coil. Here second coil to first coil. So while equating, we need to introduce a constant n1, number of turns available in the first coil. V1 equal to n1 d pi 2 1 divided by dt. Equation number 4. Now we have two equations, equation 3 and 4. This left hand side is equal, so we can equate the terms available in the right hand side. So from that, equation 3 and 4, m di2 divided by dt equal to n1 d pi 2 1 divided by dt. So dt got cancelled. M di2 equal to n1 d pi 2 1. From that, m equal to n pi 2 1 divided by di2. If permeability is constant, we can write the term m equal to n1 pi 2 1 divided by I2. So the important thing is mutual inductance is based on flux linkage in the first coil divided by current in the second coil. That is the important thing, because second coil is energized and current is flowing through the second coil. So you can compare these two. This is flux linkage in the second coil, current in the first coil. Flux linkage in the first coil, current in the second coil. So based on that, we can have a definition is available. Mutual inductance between two coils is defined as the rate of induced magnetic flux linkage in one coil. This is nothing but induced magnetic flux linkage. These two terms is the magnetic flux in coil to current through other coil, right? So N1 means here I2, here N2 means here I1. So that is the important thing. In self inductance, both are same, only one coil. In mutual inductance means magnetic flux linkage in one coil, current flowing through in another coil, right? Now we got two expression for mutual inductance. Now we'll go to the coefficient of coupling. So the coefficient of coupling K is nothing but the fraction of total flux produced by one coil linking a second coil is called a coefficient of coupling. That is K equal to pi 1 2 divided by pi 1. That's a fraction of what is the total flux link produced in the one coil and how much it is linking with the second coil. Pi 1 2 divided by pi 1. The ratio is nothing but coefficient of coupling. This is the total flux produced in the first coil. In this, how much flux is linked with the second coil, pi 1 2. So pi 1 2 divided by pi 1 is nothing but coefficient of coupling. From that we can write, you cross multiply these two. So pi 1 2 equal to K into pi 1. Similarly, in other case, when the coil 2 is energized, pi 2 1 divided by pi 2. So from that, pi 2 1 equal to K into pi 2. Right? So the coefficient of coupling means how it is linking, how much is fully coupled mean entire flux is linking. If 70% mean only 70% of flux is linking. We can find the ratio, how much of flux is linked, how it is coupled together. That can be calculated from the coefficient of coupling. Right? Now we got to have two expression. Pi 1 2 can be written as K into pi 1. pi 21 can be written as K into pi 2. Now we'll refer the mutual inductance. There are two expressions available for mutual inductance while referring coil 1 and coil 2. If coil 1 is energized, this is the term. If coil 2 is energized, this is the term. N2 pi 12 divided by I1. N1 pi 21 divided by I2. Now we will multiply on both the side. Both left hand side and right hand side terms are multiplied. M into M square. Then we need to multiply these two terms. N2 pi 12 by I1. N1 pi 21 by I2. Right? Both left hand side and right hand side are multiplied together. So M square equal to N2. This pi 12 can be replaced as, this pi 12 is nothing but K into pi 1. Similarly, pi 21 is K into pi 2. Right? So this pi 12 is now replaced as K into pi 1. Pi 21 is replaced as K into pi 2. Right? Now we have 2K available. So it becomes K square. Right? And the coil 1 terms are written separately, coil 2 terms are written separately. Right? For example, this N1 pi 1 by I1. N2 pi 2 by I2. Right? Both coil 1 terms and coil 2 terms are written separately. So M square equal to K square. What is this? This is nothing but inductance. Inductance of a coil 1. N pi by I is the general formula. So that can be written as L1. N2 pi 2 by I2 can be written as L2. Self-inductance of the second coil. So from this K square equal to M square by L1 L2. Bring this term in the denominator. So K square equal to M square divided by L1 L2. What is K? Is take the square root. So M divided by square root of L1 L2. So the coefficient of coupling, so M square equal to K square L1 L2. K square equal to M square by L1 L2. By taking the square root on both the side, K equal to M divided by square root of L1 L2. So this is the expression for coefficient of coupling. From that we can find how much this coil 1 and 2 are coupled together. Right? It is always less than 1. Why? This pi 12 is less than pi 1. The pi 1 is linking with pi 12. So this value is always less than total flux. Similarly, this value is always less than total flux pi 2. So based on that, K is always less than 1. Right? Now we'll see the problem based on this self-inductance, mutual inductance and coefficient of coupling. Now we'll see the two coils available, A and B, with 800 turns and 1200 turns. Coil A have 800 turns, coil B have 1200 turns. Having the common magnetic circuit, it means coupled together. The current is 0.5 ampere in coil A produce a flux of 3 milliweber. The current flowing through the coil is 0.5, so that it produces 3 milliweber in the first coil, coil A. In that 80% of flux link with the coil B. 80% of flux in the coil A link with the coil B. Then we need to find what is L1, L2 and M. Self-inductance of coil A, self-inductance of coil B and mutual inductance. Right. Now we'll refer what are the given data available. For coil A, number of turns available, the flux available. 3 milliweber means 3 into 10 to the power minus 3 Weber. The current also available, 0.5 ampere. The K equal to 80%. That means K equal to 0.8. That is 80% of flux linked with the second coil. For coil B, the number of turns available, 1200. The flux is pi 12. The 80% of pi 1 is available in the pi 12. So 80%, 0.8 into 10 to the 3 into 10 to the power minus 3, it is 2.4 into 10 to the power minus 3 Weber. For coil 2, number of turns available, flux is available. But current is not available in the coil B. Right? For coil A, all are available. N, pi, I, all are available. So we can find the inductance of a coil A. L1 equal to N1 pi 1 by I1. Right, N1 is 800 and pi 1 is 3 into 10 to the power minus 3 divided by I1 is 0.5. So that is equal to, by simplifying, we got 4.8 Henry. Right, all the values are available, so we calculated the inductance L1. But coil 2, the current value is not available. So we'll find the mutual inductance. From that we can find coil in the inductance in the second coil. So for mutual inductance, these data are available. N2 pi 12 by I1 is available. N2 available, pi 12 available, and I1 also available. So that we'll find mutual inductance. Then we'll find the L2 value. So N2 is 1200 into pi 12 is 80%. That is 2.4 into 10 to the power minus 3 divided by current is 0.5. So that is equal to 5.76 Henry. The mutual inductance between coil A and B is 5.76. Now we have the value of L1 and M. We need to find L2. We know one more value, the coupling coefficient of coupling K is available. So from the coefficient of coupling we can find the L2 value. So M equal to K into square root of L1 L2. So M value is we calculated, K value is also known, L1 also already calculated. So from that we can calculate L2 value. So square on both the side, M square equal to K square L1 L2. So L2 equal to M square divided by K square into L1. Now we substitute the value, L square equal to M square by K square into L1. M square, that a mutual inductance is 5.76 divided by the coefficient of coupling is 0.8, 80%, 0.8. The L1 is 4.8 Henry. So by simplifying this, what we got? 10.8 Henry. The L2, the self-inductance of the second coil is 10.8 Henry. So now we calculated L1 value, then mutual inductance, then L2 value. All three values are calculated. So in this video we discussed the derivation of self-inductance, mutual inductance, coefficient of coupling, followed by one problem based on this. Thank you. Welcome viewers. In this video we'll see the Faraday's law followed by the problem. First we'll see the Faraday's law. So based on the statement that total electromotive force EMF induced in a circuit is equal to the rate of decrease of the total magnetic flux linking in the circuit. V equal to minus d pi by dt. This negative sign is indicated decreasing. So due to rate of change of flux, EMF is produced in the coil. If n number of turns available, in the circuit, then the total flux will be n into pi. So V equal to minus n d pi by dt. If n number of turns available, then we can write V equal to minus n d pi by dt. By definition, the EMF in a circuit is a line integral of electric field around a closed path. So the EMF based on in terms of electric field is given as V equal to integral E dot dl. So another form. The previous one based on Faraday's law, this is general form. V equal to integral E dot dl. According to Gauss law, the total flux passing through the surface is equal to the surface integral of magnetic flux density over the surface. So the Gauss law is given pi equal to double integral B dot ds. Right, now we got the expression for pi. Now we will substitute this pi in the equation, EMF equation. That is V equal to minus d pi by dt. In that you can substitute the value pi. So V equal to minus d by dt of double integral B dot ds. Right, this pi is now replaced with the Gauss law, expression given by Gauss law. Magnetic flux density, in terms of magnetic flux density, V equal to minus d by dt double integral B dot ds. So V equal to, that can be written as V equal to minus integral dB by dt into ds dou b by dou t, partial differentiation. But V also expressed as E dot dl. Now we can replace this V as E dot dl, so that integral E dot dl equal to minus double integral dou b by dou t into ds. Right? Now we got the expression for this electric field intensity in the single integral to double integral. So by Stokes theorem, this E dot dl equal to double integral del cross E into ds. Right? So the E dot dl from the Stokes theorem is given as del cross E into ds. So by comparing these two equations, this left hand side is equal, so we can equate the terms in the right hand side. Right? So double integral del cross E ds equal to minus double integral dou b by dou t into ds. So integral available on both the sides, so that can be written as del cross E equal to minus dou b by dou t. So we got the expression in terms of electric field, magnetic flux density, del cross E equal to minus dou b by dou t. This is also referred as a Maxwell's equation. Now we analyze the Faraday's law. Finally we got the equation that is termed as Maxwell's equation. Now we'll see one problem. Now we'll see this problem. A square coil with loop area 0.01 meter square. The area of this square coil is 0.01 meter square and having 50 turns is rotated about its axis at right angle to the uniform magnetic field of 1 Tesla. Right, one square coil with area 0.01 meter square with 50 turns available. It is rotating about its axis at right angle to the uniform magnetic field of 1 Tesla. We need to calculate the instantaneous value of EMF induced in the coil. We need to find induced EMF for 3 different conditions. At right angle to the field, at 45 degree to the field, in the plane of the field, right? And speed of rotation is given as 1000 rpm. Right? Now we'll see the data. What are the given data available? Area is 0.01 meter square. Number of turns is 50. The magnetic flux density is 1 Tesla. The speed of rotation is 1000 rpm. Now we know that E equal to minus n d pi by dt. This d pi is nothing but pi m cos omega t. Right? So we need to differentiate with respect to t. So minus n, this pi m is constant. The differentiation of cos omega t is minus sin omega t into omega, because here omega t is available, so into omega. So here 1 minus, here 1 minus is there, so it become plus n pi m sin omega t into omega. That is E equal to n b a omega into sin omega t. So this pi m is written as B into A, magnetic flux density into area, because pi m value is not available, B and A value is available, area available and magnetic flux density available. So that n pi m is written as B into A. Actually B equal to pi m by A, so pi m equal to B into A into omega sin omega t. Right? So by using this formula we can find the induced EMF for 3 different conditions. So first right angle to the field, that is omega t equal to 0 degree. Right? In that sin 0 is 0, so totally the value will be 0. 0 degree. Due to 0 degree the induced EMF will be 0. Next one, at 45 degree of the field, that is omega t equal to 45 degree. So in this what we need is omega value is needed. So omega equal to 2 pi n divided by 60. So 2 into pi into n is number of speed of rotation, 1000 divided by 60, so 104.7 radian per second. So we can substitute all the value. N is available 50, B is the 1 Tesla, area is 0.01, omega value we calculated 104.7 into sine omega t, that is sine 45 degree. So by simplifying all, what we got? 37 voltage. E equal to 37 voltage. Now if in the rotation in the plane of the field, that is omega t equal to 90 degree. Right? The same thing we can substitute n b a omega into sine 90 degree. Right? The all values are substituted. For sine 90 is equal to 1. So E equal to, by simplifying this, what we got? 52.3 voltage. Right? Now we got the induced EMF for all three cases: right angle, 45 degree and 90 degree. So in this video we discuss about the Faraday's law in terms of electromagnetic theory. We got finally the Maxwell's equation and we solved one problem. Thank you.